Well, I'll comment that there's a slight title change. Was dual laser weathered, now it's going to be long pulse laser weathered. Okay, so first I'll just start by thanking Survey and my collaborators and the Institute for Rock Magnetism, where I did the bulk magnetic properties. So the magnetic properties of lunar soils and the weathered and laboratory weathered materials are very important because this is where space weathering forms nanophase iron particles. So on the left, we see a vapor deposited rim that has sub 10 nanometer iron particles. In the center, we have a figure of a TEM section of a lunar agglutinate, which shows micron sized particle, but the particles in agglutinates tend to be at least twice the size of those in the vapor deposited rims. And there's a pronounced effect on the optical spectra that are shown in the black trace on the right, where we see a loss of a spectral contrast of mineralogy, a reddening, and lower albedo. So other laboratory weathering simulations have been done in the past, usually using short pulse lasers, 10 nanosecond, and this is very effective at producing nanophase iron in amorphous rims and vapor deposited rims. However, few agglutinates are formed, and those affect the albedo more strongly. So our goal in this work has been to try to produce more agglutinates using more energy and long pulses. So at Washington University, Jeff, you built a system that combines two lasers for the dual laser weathered system. We'll talk on that another time. Where the short pulses, the idea is to create vapor deposits to make the rims, and the long pulses to create melt deposits to form these glass welded aggregates we call agglutinates. So that's the focus of this talk. So on the left figure, we see a laser agglutinate made by the long pulse method, and we compare that visually to the lunar agglutinate, and they appear similar. On the right-hand side, the reflectance spectra evolved from San Carlos Olivine down to 32-minute long pulse laser weathered sample, which shows the evidence of a very mature, optically mature material, particularly very low scattering. By comparison, the light green trace in the middle is the accumulation of short pulses, and it isn't nearly as mature optically, at least, as the long pulses. So what is the particle size distribution of the iron in the agglutinate? And so we're looking at a TEM fib section, which shows a couple of features. For example, there's a glass bead lying on top of a recrystallized olivine grain, and the white specks are, of course, the nanophase iron that occur in the rims on the outer side. They're underneath the glass bead, varying particle sizes. And so this very much simulates, or it resembles, what lunar soils look like. And the size distribution on the right is sort of broken down into two regimes, really, from greater than 50 nanometers, which is the long bar on the right-hand side. There's almost 200 particles counts out of 1250, 1260 of the larger particles greater than 50 nanometers in diameter, and the rest are the sub 50 nanometer nanophase iron particles, and they're broken down magnetically into the different regimes, such as superparamagnetic, less than 10 to 15 nanometers, intermediate size, 15 to about 30 nanometers for the single domain magnets that survive up to the Curie temperature, and then multi-domain are greater than 50 nanometers in size. And so I've also included sort of the effects where the smaller particles redden the sample, whereas the larger particles decrease contrast and darken the sample. So we've been studying this by ferromagnetic resonance spectroscopy, from which we can calculate the maturity index. And so here's a spectrum of Amare soil and some of the parameters of it, such as the peak-to-peak line width and the amplitude, G-value, and so on. Now, the maturity index by Morris uses the intensity of the ferromagnetic resonance signal normalized by the weight percent iron oxide in the sample, because there's a dependence on intensity versus the iron in the regolith. And so we calculated this for our laser weathered samples by comparing it to a lunar soil. So we calculate the lunar soil, and these are relative to that. Notice, keep in mind that the ferromagnetic resonance detects the superparamagnetic and single domain nanophase iron and not the multi-domain iron. One of the advantages of this maturity index is it doesn't saturate with exposure in principle. So here on the left, we're looking at the FMR spectra of the 32-minute laser weathered material, comparing the bulk and the hand-picked agglutinate fraction from the sample. Notice that the agglutinate is about half the intensity of the bulk. In the center, we compare the maturity index on the left to the laser weathering time on the abscissa, and we see that the bulk increases linearly, the bulk maturity increases linearly with time, whereas the agglutinates actually decrease with time. This isn't so hard to understand, but what it means is that the linear increase means that we're just making single domain superparamagnetic particles, right, with time, whereas in agglutinates, we're making larger particles, multi-domain. And so those are not captured by ferromagnetic resonance. So the agglutinate fraction carries less superparamagnetic single domain, less than 50 nanometer particles than the bulk. Okay, so looking at the bulk magnetic properties, and of course, these were always studied in the lunar soils back in the 70s. There's a lot we can learn from the hysteresis measurement, where we start from positive saturation, go to negative saturation, then back to positive saturation. And here are two graphs just as an example. For example, we see that the saturation magnetization, that is the total bulk iron that is in the sample, either the bulk or the agglutinate fraction, increases with time. Whereas we compare that to the saturation remnants. Now the saturation remnants is carried only by the single domain magnets, and that also increases linearly for the bulk, but the agglutinate is less, right? We have more multi-domain, and so it doesn't carry a remnants. So here's a table of some numbers that just compare it to the lunar soil 71501. Lunar soils typically have about 0.5 weight percent nanophase iron in them, and we haven't quite made enough in this particular sample set. But the takeaway is that we have too many multi-domain particles, not enough single domain particles sort of to match the profile of the lunar soil, at least at this point. Now, there's more that we can discover and uncover about lunar soils and the laboratory weathered materials by looking at what's called the first order reversal curves. And this is a relatively new technique that's really come into prominence in the last 20 years, where instead of the zero order curve is the full saturation, the hysteresis, but a first order curve starts at saturation and doesn't go all the way to negative saturation. It starts at some intermediate value and then returns to saturation briefly. And that results in a set of first order reversal curves shown on the upper right. By taking the mixed second derivative and a grid of evenly spaced points, we arrive at the grid at the bottom, and the amplitude of those points turns into a contour plot. And the contour plot allows us to look at the agglutinate fraction, lunar soils, or other return samples that show the dispersion in nanoparticle size, shape anisotropy, and possible interactions. So for example, here at the origin, where we see the superparamagnetic and single domain magnet fraction that are spherical in shape, there's the largest part of the contour plot. We see a long coercivity tail, which indicates shape anisotropy of the single domain magnets. Here along vertical axis is indication for multi-domain nanophase iron. And finally, here in the center, the breadth of the horizontal axis indicates nanoparticle interactions. So there's a lot that could be learned from first order reversal curves. When we compare the Mare soil to the bulk, they are similar in appearance and they carry some features, abundant superparamagnetic single domain iron, a little bit of multi-domain iron, and a mixture of magnetocrystalline and magnetostatic anisotropy, that is spherical versus shape anisotropy in the particles. But the lunar soil has very little interparticle interactions. So to summarize, agglutinates are very important to help capture the optical maturities. This is about studying the maturity and the formation of the nanophase iron. And we have a way forward, we think, by using a combination of short and long pulses to arrive at, understand better how the nanophase iron forms in relation to and its effect on optical maturity. Thank you.
Thank you, Andrew. Do we have questions in the room or online?
That was really interesting. Thank you. Is this on?
It's coming through, I think.
Okay. Did you manage to play around with the power of the laser? I know you talked about duration, but are there other parameters you can play around, and how does that affect the production of agglutinates?
Oh, well, that's a great question, and that's kind of the next set of tasks, right? We've done just the short pulse, the long pulse, and then we can play around with the laser pulse time, and as well as the mixture between the short and long pulses. So we haven't done that yet, but that's right at the top of our to-do list. Thank you.